Welcome to videos on data converters. In this video we shall see examples of flash ADCs. So this is part 10 of data converters. So let us consider a 3-bit flash ADC where the output is 3-bit. So as we know that flash requires 2 power n minus 1 uh, comparators. So meaning 2 power n is 8. We are supposed to have 7 comparators. So we have 1, 2, 3, 4, 5, 6, 7 comparators. The corresponding output voltages are V01, V02, V03, so till V07, and we are getting the required reference voltage for each of the comparator from this resistive differentiate, potential divider. So starting the bottommost as 0.5 R, and each voltage, that is V1, V2, V3, separated by 1 LSB. So at the topmost we have 1.5 R. So we know that since we are assuming a reference voltage of 5 volt, and since the number of bits are 3, so 1 LSB corresponds to 0.625 volts, that is 625 millivolts. Now we know that we can actually find out what is the voltages at different nodes, that is V1, V2, V3. So for that, let us find out what is the current that is flowing through this resistive network. So current is given by V reference divided by 8R, because if we sum up all the resistors from 0.5 R and this is R, suppose if we sum up all the resistors, so it comes out to be 8R. There are 8 resistors. The extreme one is 0.5 and 1.5 R, which happens to be 2R, and we have another 6 resistors in between those two. So the current happens to be 0.625 divided by R amperes. Now we can actually find out what is the voltage at V1, which is nothing but the current flowing through that multiplied by 0.5 R, which happens to be 0.125 LSB, 0.125 volts, which happens to be exactly half LSB. So V2 is actually the voltage at this point where the resistance is R plus 0.5 R, which happens to be 1.5 R multiplied by the current. So this comes out to be 0.9375 volts, so which is corresponding to 3 by 2 LSB. So similarly we can find what is the voltage from V1 to V7. It is interesting to note that all reference voltages are odd number of half LSBs. So this is 1 half LSB, 3 half LSB, this is 5 half LSB, and this is 7 half LSB, like that. So as we can see here, so this is voltage V1 to V7, and these are the corresponding voltages in terms of LSB. Now let us see these are the reference voltages for this comparator. The other input for the comparator is the V input, that is V in. So let us see how do we what is this V01, V02, V03. V01 is nothing but the comparison of V1 and V in. So that's what is we have a when V in is between 0 and V1. So we have that when V reference is always constant, so that V1 to V7 will be always constant for a given reference voltage. So that is given by half LSB, 3 by 2 half LSB, and 5 by 2 half LSB. So input can be any voltage. Now depending on the input voltage, suppose the input lies between 0 volt and V1 volt, we're going to have all comparator outputs will be 0, 0, 0. So corresponding to this all 0 input for the decoder output should give 0, 0, 0. Now if the input voltage is between voltage V1 and V2, only the first comparator output is high, so which should give a 0, 0, 1 as the output combination, as the output resultant for that input voltage between V1 and V2. So likewise, if the input voltage between V4 and V5, so we're going to have the bottom 4 comparators output will be high, the other 3 comparator output are low now. So this should result in a output voltage of 100. So likewise, for different input voltages, depending on what is its value compared to the reference voltages, we will have the input to the decoder, which happens to be the output of the comparator, and the output of the decoder will represent the digital equivalent of the input voltage. So this is how it looks like now. If the input voltage is between 0 and V1, if it is between 0 and V1, we're going to have the output voltage as 0, 0, 0. If the input is between V1 and V2, so as we saw in the previous here also, if the input is between V1 and V2, so the output voltage should be 0, 0, 1. So that's what is 0, 0, 1. So you take this condition where the input is between V4 and V5. So just go back to this and see, if the input is between V4 and V5, we have to have 1, 0, 0. So let us go back to the transfer characteristics and verify when the input voltage is between V4 and V5. That is, when it is between V4 and V5, we are supposed to get the output voltage as this is 1, 0, 0. So you can just go back and see, when it is between V4 and V5, we are supposed to get it as 1, 0, 0 as the output. So let us see here, when it is between V4 and V5, we have an output voltage corresponding to 1, 0, 0. So likewise, we have the output making a transition whenever the input crosses odd number of half LSB. That is, this is the first half LSB, this is 3 half LSB, 5 half LSB, so on so. This is what we saw in the ADC characteristics in the basic videos. Now, suppose if we have, instead of having it as a 0.5 R, suppose if we have it as just R. So what is, if the first resistor is R instead of 0.5 R, so we're going to have different voltages for V1, V2, V3. Now you can see in the earlier case, V1 was actually 0.3125 volt, which happens to be half LSB. If you replace this 0.5 R by R, this happens to be 1 LSB, 2 LSB, 3 LSB. The difference, what happens if you are replacing the bottommost resistor by 1 R and this is also by R. Now instead of having it as 0.5 R and 1.5 R, if you make this R and this also R, we end up with the voltages at V1, V2, V3 as LSB, 2 LSB, 3 LSB. Now the transition will not happen at odd number of half LSB. It will actually happen for even number of half LSBs. Meaning to say, so in our transfer characteristics, this will going to be there till, so this V1 will going to shift to 1 LSB, V2 will going to shift to 2 LSB, V3 will going to shift to 3 LSB. So these transitions will shift from this odd number half LSB to even number half LSB. So that is the only difference we're going to have if you replace the bottommost resistor by R and the topmost resistor also by R. So we should always ensure that the sum of the resistor happens to be 8R, because we have 7 reference voltages which corresponds to different, because we have 7 comparators. In order to have 7 reference voltages, we need to have 8 resistors. The sum up of all the resistors should be equal to 8R only. So we cannot have R here and we cannot have 1.5 R. Suppose if you're making this R, so this should also be replaced by R. If that is the case, we'll end up with there is a shift in the transfer characteristics from half LSB to 1 LSB. So transition of your output will change from odd number of half LSB to even number of half LSB. So that's the major difference if you change these reference voltages by using different values of resistance. That is, instead of 0.5 R, if you replace it by R. So let us take up an example. In this case, okay, we are treating the bottommost resistance as 0.5 R and the topmost as 1.5 R. And we have been, we'll just verify what is the digital equivalent for 2.3 volts. Suppose if the applied voltage is 2.3 volts and if your V reference is 5 volts, now we can actually find out what is this 2.3 volt corresponds to. So this 2.3 volt lies between, suppose if you just go back and see, so this is, so we are looking at 2.3 volts. So you can see now 2.3 volts is actually lying between, we can actually find out what is that. I just ask you to find. You can see now 2.3 volt lies between V4, which happens to be 2.1875, and V5, that is 2.8125. See now 2.3 is in between these two voltages. So V4 is less than 2.3 and 2.3 is less than V5. So V3, the input voltage is lying between V4 and V5. So since V4 is less than V3, we're going to have V04. Till V04, all the comparator output are high, high, high. So you can see this is high, this is high, this is high, this is high. Why all the four are high is because for comparator starting from the bottommost, second, third, fourth, the input voltage is more than the reference voltage. When the input voltage is more than reference voltage, we know that as per the connections we have given for the comparators, see here, if the input voltage is more than the reference voltage, so V plus is more than V minus, we are supposed to get V01 as high. So what we have considered is 2.3 volt. So 2.3 volt is certainly more than this V4. So this is 2.3, 2.3, 2.3, 2.3, and we have V8 as, so V8 is actually is equal, sorry, V4 is actually equal to 2.1875. So we have till this point, till V4, the input voltage is more. So since V plus is more than V minus for the bottom four comparators, we're going to have V01, sorry, V01, V02, V03 and V04 as high voltages, whereas V5, V6, V7 are all more than the input voltage. When V5, V6, V7 is more than the input voltage, so here for the topmost three comparators, V minus is more than V plus. So naturally we're going to have V01, sorry, V05, V06, V07 will be of low voltage. That's what we are having here. V1, V2, V3, V01, V02, V03, V04 are high because the bottom four comparators have their input voltages where input voltage is more than the V minus. So V minus is actually reference voltage. But in the top three comparators, the input voltage is less than the reference voltage. That's why we have 0, 0, 0. So corresponding to this input combination for the decoder, decoder will give 1, 0, 0 as the output voltage. So a 2.3 volt will result in 1, 0, 0 as the output voltage. This will happen in only one clock pulse because whenever we give the clock pulse during the positive rise of the signal, the comparator will give this output voltage of 1, 1, 1, 1. The bottom four comparators will give 1 and the top three comparators will give 0. Upon the falling edge of the clock, the decoder will give this output, that is 1, 0, 0 as the output voltage corresponding to 2.3. Similarly, let us find out for one more input voltage of 3.6. Of course, you can find out. So this 3.6 lies between V6 and V7. Since it lies between V6 and V7, so till V06. So this is V06. So V0 till V06. That is bottom 6 transistor, comparators will give their output as high. Only the topmost comparator will give an output voltage of 0. So corresponding to this 0 and the bottom 6 comparators are 1, will end up with the output voltage of 110. That's what we saw in the truth table. If we have only the MSB as 0, that's what we have. If MSB is 0 and if all other bits or all other comparator outputs are 111, so we're going to have 110 as the output voltage. So that's what we have it for the second example. In the second example, you can see except this, all other bits are high. So we'll end up with B1, B2, B3 as 110. Similarly, you can try out for an example where the input voltage is 1.1 volt. So this 1.1 will be lying between V2 and V3. We can actually find out what is V2. V2 is actually this is 1.5 LSB. So 1.5 LSB and this is 2.5 LSB. So where LSB is 6, how much is LSB now? So LSB is 625 millivolts. So considering V reference as 5 volts, the LSB happens to be 625 millivolts. If it is 625 millivolts, now it is 1.5 into 625 millivolt. Here it is 2.5 into 625 millivolts. This 1.1